Hey guys, how's it going? So today I'm going to briefly go over differential forms in algebraic topology, just kind of like a little bit of a tour. Um, Most people on the first time reading this through just kind of see this algebraic topology thing and they'll be like, yeah, this is a topology book. But not necessarily. In fact, we're going to choose a very leverageable approach to the subject that basically makes algebraic topology extremely digestible because we start with differential forms. And it's important to do this specifically with the rham cohomology. First of all, to start with that, because it kind of just shows you how calculus and topology are not really separate subjects to begin with, and we talked about differential forms in Sternberg's lectures from our previous endeavors, but with the stupid clickbait title. Warm me up my Neuralink or whatever. But you have the calculus, and then calculus is going to get motivated uh, pretty early on here. Where is the table of contents? Here it is. Yeah, so we'll go through the rham complex. And it basically just starts with the fact that calculus gives you geometry, but then geometry allows us to, with Poincare lemma, we get this kind of transition from geometry to more using more topological language to describe some types of mathematical phenomena. And then we'll move on to ways to actually algebraically count, and compute these cohomology itself with the Viator's types of principles by discrete counting, so that you get like these algebraic type of correspondences. That's why it's called algebraic differential forms in algebraic topology. So that's chapter 2. And then the spectral sequences allow further computational types of techniques. We're going to be concerned with bundles and homotopy as well. The homotopy theory itself allows us to describe more nonlinear phenomena that emerge because of unfortunately, the language that we use with cohomology is fairly, limited to describe these more types of topological fields. And then in characteristic classes, you have the splitting principle, flag manifolds, Pointryagin classes that deal with real bundles, and then Chern classes for complex vector bundles. This basically is just, all of this then is the foundation for gauge theory, for mathematical types of gauge theory as well as physics. But you basically, the deeper reading of this book essentially is just because you'll skim through it. I've skimmed through it like a couple times already. I've worked a couple problems, but really you want to look at how the differential structure becomes global information. That's something that really stuck out to me as a physicist. Okay, so the central question of this entire book is how much global information can be extracted from local differential data. And let's just go ahead and go to, so there's de rham theory, de rham complex. Yeah, let's just go ahead and go to the first chapter, de rham theory. Yeah, here we go. Here we go. Man, I'm kind of deep in the chapter. Sorry. So there's a couple of things that should be known. Oh my god, it's pretty annoying. I don't know what the hell is going on here. The rham theory. Come on. It's so laggy. But anyways, um, we're here. We made it. To the de rham theory. Okay. So the differential form is going to be defined here. And we had a proper treatment of this from Sternberg's lectures in differential geometry. Holy crap, Jesus, what is happening? I mean, I'm not running anything in the background. My memory's fine. Anyways, um, jeez. So okay, exterior differentiation, right? We it's an anti-derivation from a graded exterior algebra. Okay, and that graded exterior algebra, I mean, you can develop multilinear algebra in the first chapter of Sternberg. Okay, that's all you need. And what's going to happen is the exterior derivative is going to have this quality, um, and the quality is that it's anti-derivation. But it's also nilpotent. So this is going to make sure that your divergence of your curl is 0 and your um, crap. Oh, your curl of your gradient, right, is also 0. All of that's going to be contained within this, and it's basically just this kind of it's just an algebraic statement. That's all it is, and it's the entirety. It's how you birth the entirety of cohomology, which cohomology is just the idea of having closed Q forms. If you remember, for something to be a closed form versus an exact form here, because of how we built, Stokes theorem. Let's see. Yeah, so we have zero forms. Zero forms, you can think of them as like potentials, or like just like some kind of electric potential, basically. And then one forms, they're vector potentials, or circulation, if you will, or the circulation of a mathematical vector field. However, if you want to use physics or math, I don't care, as long as you get that. And then magnetic flux, or just field strength, the strength of some field, and then like some density, charge density, mass density, whatever. Okay, and what this algebraic statement here of the d squared being equal, the exterior square of the exterior derivative operator being equal to 0, that is gauge invariance and conservation. So basically, conservation laws. And this what comes out of this is the nice uh, where is it? Jesus. Here, the cech-de rham cohomology of Rn is the vector space, where you have closed Q forms. You're taking the ratio of the closed Q forms divided by the exact Q forms. And it's basically just the kernel. I mean, it's basically the kernel of this operator divided by the image of the operator. Okay? There's a couple important theorems that I'll just briefly talk about. There's Poincaré's lemma. And Poincaré's lemma is this. And it says that, the cohomology is equivalent to 0 for Q is greater than for the Qth cohomology greater than 0, it evaluates as 0. Okay? And this mathematically guarantees that closed forms are locally exact, and establishing that the local triviality is underlying all of the continuous geometry that we're talking about. Okay, so that's the Poincaré's lemma. It's pretty simple. The Meyerowitz-Horst sequence, I think that's next somewhere. Yeah, here it is. So that's basically like, if you just have like a long sequence relating all the cohomologies of a global space to the cohomology of local open covers, you can basically have this computational, it's just computation. And you can induce, or you can have this inductive engine for the geometric topology of whatever you're looking at. So, of course, you can develop this mathematics by reading and working through problems. But yeah, it's just kind of a nice fundamental technique, right? And then there's Poincaré duality. Yep. So Poincaré duality is this is for non-compact manifolds. There's just a regular. I don't know when the first time it's mentioned. But Poincaré duality just says, like, if you have a non-degenerate pairing, it's for orientable manifolds. That's right. Where the hell? Let's see. Poincare duality. Let's find it. Taurus. Yeah, here we go. It's yeah. Okay. Um, that's early on. Oh, here we go. Here's what I'm looking for. So, yeah, if your pairing is degenerate whenever the manifold is orientable and has a finite cover, it doesn't matter. Doesn't matter what your in is, right? For an orientable manifold of dimension n, they are isomorphic to each other, right? And so it's a non-degenerate pairing. So you have a profound symmetry in the topological structure of smooth manifolds themselves. That's a super important thing to realize. So that's why I was taking so long to ensure that. We also have tome isomorphisms. So let's go to the tome. Yeah, tome isomorphism. We have a vector bundle, and this is a very structural result. That's nice, but you have an oriented ring in vector bundle. Um, over the manifold, then you can also have a similar type of isomorphism as well. So he's just like straight up just giving you all the isomorphisms. And this relies on the tome class, which is it's a complexly supported vertical cohomology class that depends on some distribution. What is it? You need a localization. I think I need to show about the localization principle as well. Let's see. Localization. So the support of the Poincare dual of the submanifold can be shrunk into any tubular neighborhood of S. That just allows you to do is just allow you to bridge differential topology with the theory of distributions and delta functions, so that you can talk about these types of distributions at particular locations very nicely. Okay, so of course, then they're complexly supported. So if it's compactly supported, then the distribution disappears. Topologically at a certain edge, if you will. Okay. Now, that's pretty much all I really need to go over. Let's move on to the next one. Let's go cech-de rank complex. So the primary structural vehicle we're going to use for the cech-de rank complex is something called the double complex. And what it's going to do is it's going to build local differential forms along cech cochains. And it's going to be equipped with something called the exterior derivative, and it's going to operate vertically with the cech difference operator. Now, acting horizontally. Now, what's nice about this is you get this kind of like little tic-tac-toe type of lemma that's later in the chapter. But what it does is it gives you some algorithmic type of correspondence between the differential geometry and being able to play around with the algebraic combinatorics associated with it. So really, the Euler class and the Hopf index theorem dictate that the Euler characteristic is going to act as an absolute geometric obstruction to the existence of non-vanishing vector fields on a manifold. And so we can we can have some. That's really all that the content in this chapter is, just really understanding the consequences of the exterior derivative acting vertically and the cech difference operator acting horizontally. and that's really what's happening here. Um, that allows for just allowing us to compute and have different explore the methods of like how these differential forms are behaving, and of course also we could the check difference operator will also basically this is true because we emit two indices twice with opposite signs, and then he just kind of justifies it. But yeah, so this little delta squared, these this allows us to have these nice check cochains in topology because oh, also I didn't go over the idea of a good cover, so let me do that real quick. That's probably important as well. Um, so yeah, the whole idea is that if you have a bunch of open subsets, but they're finite, so because we were on continuous manifolds, but we want to go to discrete types of combinatorics, and this is really where the algebra of topology comes from, because as we try to see, yeah, exactly. Good cover than all ignorant. Okay, so if U is a good cover of the manifold, then the de Rham cohomology is isomorphic to the cohomology of the good cover. I don't know where the hell the definition of the good cover is. My thing is being so my control F is being so laggy, but basically you're just covering a manifold with open sets, where you have like every single non-empty finite intersection is smoothly contractible. So you have like some analytic data from some differential forms. You can just mirror it by the discrete combinatorial data of the cover. That's all it is. It's very deep. I know I'm just saying that, but you get this. The continuity of the geometry becomes discrete algebra. So that's very nice. Um, Now the Euler class gets introduced as well with sphere bundles, which is super important for physics because um, basically within the cech-de rham theory, or the cech-de rham theory form, the language of you have Dirac monopoles, holonomy, and higher like form symmetries. That can be described by fiber bundle or sphere bundle, if you will, that is oriented um, with rank in vector bundle, and the creation of that Tom class will require specific construction of an angular form with a complement of a zero section, and so that's what happens here. But because the global bundle may be twisted somehow, it's not globally close, so you're going to need an exterior derivative that measures the topological twisting of the bundle, where E is the Euler class of the bundle. Okay, so you'll get p-form gauge units winding in transverse geometric space. This also has consequences for structure groups. And there's a couple results that come out of this. So yeah, if we consider a circle bundle with a structure group, this is like basically the language of instantons. But if we wanted to look at the trivialization of a U1 bundle, which I don't know if they compute that in here. Last time I checked, it's just the general construction. That'd be a good exercise. But if you just take the U1 principal bundle with an angular form, and you would take the vector potential on the local coordinate patches, glue them together by gauge transformations, and you'll get these nice you get this nice solution where you avoid a Dirac string that's like piercing through the entire universe. Instead, like you kind of patch it together, and yeah, it's nice. It's just it's a nice representation of U1. So the Euler class E is independent of the choice of a good cover. So it's like the Euler class itself has this nice property as well. And of course, you would have to prove that. But you get these. Really, we're just leveraging the de Rham isomorphisms. So, and keeping track of those types of invariants, topological invariance. Now let's move on to, I think it's time to move on to the next chapter, which is would be on spectral sequences and some more applications. So, while the rham theory provides an analytic framework, it's failing to detect torsion, all right, or just a twisted, discrete integer phenomenologies of topology. So if we want to classify geometric spaces, integer coefficients can become very strictly necessary. Homotopy itself becomes unavoidable. So now we need to find a way to repair torsion defects. So we can start with something called a page, if you will. Let's see. Let's go. Let's move on. Abelian groups. Okay. The differential complex. So it goes through complex. Going to be chasing diagrams to compute things. I mean, this is very analogous to like renormalization, where you keep like iterating some type of operator in a certain way to then get the full sequence itself as you go to E infinity. Here we go. Yeah, stationary value E. Okay. Let's go to a page. Filtration. That's also the other word that gets thrown around a lot. But a filtration K is a filtered complex. It's said to have length. This for the same argument. It's customary to write E R for BR, so sequence of differential groups. A graded filtered complex. Yeah, so with an initial type of like with a page in general. So let's just say a filtered complex. And it's just kind of a coarse approximation. Usually some kind of cohomology of a base space that's censored with the cohomology of a fiber and a fibration. And then you'd have a sequence of differential groups. And themselves, this sequence of differential groups can eventually converge to something like E infinity. And this would be a graded group of some filtered group H. That we'd say now the spectral sequence converges to H. Now, you would get you can derive a bunch of results out of this with like the spectral sequences of a fiber bundle, the Jensen sequence, properties of exact couples, there's path vibrations, the cohomology of loop spaces. So that's just the beginning of modern homotopy theory. So that's very nice. Well, I mean, and then the math just kind of goes on and on and on and on. But we got to make sure that we are like, doing the correct mathematics. Okay. So in order to do that, we have to think physically about what's happening when we iterate a spectral sequence topologically. Okay. And again, working with these double complexes. Actually, I'm going to screenshot this for the video though. It's kind of cool. I like that. Okay. Anyways, what is this? This is a spectral sequence. Oh, it's just the spectral sequence of a double complex. Summing three elements. Okay. Yeah, that's pretty neat. And of course, we're just working with the cochains, or with the check cochains, which is pretty cool. But anyways, so the spectral sequence is going to act like a topological equivalent of the renormalization group flow. So just as renormalization group in physical systems, you have finer energy scales with effective long-range dynamics. Like the standard model, relies on renormalization. The differentials are going to represent interaction terms. You can think of like physical anomalies of this Arth scale, so like topological types of data. And the topological class, then, if a topological class survives all differentials to reach E infinity, then it represents a stable global invariant observable of the physical system itself. So, and this will motivate something called Moore's theory, which later in this chapter it connects, critical points, topology, variational physics. But in the 1980s, this was revolutionized when Moore's theory was applied to supersymmetric quantum mechanics. And the critical points of the Morse function correspond to the classical vacua of supersymmetric theory. And you can have like very nice computational means of finding gradient flow lines between critical points and instanton tunneling itself. So, and if you're unfamiliar with what an instanton is it's basically like a fundamental solution to that can be used to describe basically standard model. It's like soliton that's gauged on a soliton solution to a system that's like gauged on a structure group. Okay. So that's everything. So you just talk about higher differentials, initial pages, and how they we get this local type of smoothing, and then how it converges, and we can get like stable types of renormalized stable observables, and then basically it just reduces a lot of symbolic algebra as well. So we can explore a bunch of this, or you can explore a bunch of these different phenomena. But let's move on. So basically, let's move on to the characteristic classes. Yeah, characteristic classes. Now, these represent really the ultimate destination of the synthesis between this kind of allows us to not bookend the book yet, but allows us to get to the apex of what we're talking about when we are looking at differential forms and algebraic topology as kind of a single intersection subject, because it's going to position characteristic classes itself as the exact cohomological agreements of the global twisting of bundles. So if you have the Euler class mathematically, or we're starting with the Chern class, but if you had an Euler class mathematically, how it measures the obstruction, finding a single non-vanishing section of a bundle, the characteristic classes, so Chern classes for a complex vector bundle, Pointryagin classes for real bundles, they measure the hierarchical obstructions defining multiple linearly independent sections. Okay? And the existence and uniqueness of Chern classes form this kind of structural baseline, and with a computational trick that underlies pretty much every practical characteristic class calculation is something we call the splitting principle, right? And let's find it. Yeah, so the splitting principle. All right. So what the splitting principle is, why it's really important, is that any polynomial identity involving Chern classes holds for a sum of line bundles, or for a direct sum of line bundles, that holds rigorously for all vector bundles. So one can algebraically pull back any complex vector bundle over M to a flag manifold, where the bundle is completely and cleanly splits into a direct sum of line bundles. And so that's the entire geometric theory of the classical classification of vector bundles. Just classifying vector bundles in general, because it establishes that every rank in vector bundle over a manifold, specifically via a pullback on a universal quotient bundle over an infinite Grassmannian. That's kind of where it heads to, but the characteristic classes are not these kind of just invariants, right? They're not just some like arbitrary topological invariants. They're the only natural cohomological invariants of a vector bundle itself. And so studying vector bundles is very interesting, and for topological fields and such. Now this isn't related to the book, but there's also spin vectors and spinners and spin geometry as well that changes the behavior of how flag manifolds move around and stuff. But yeah, that's just also another thing that's pretty cool, that I think is pretty cool. Now, when we, I think we can safely, synthesize pretty much everything. You have the Pointryagin classes. Um, I mean, you can go in and read all these things, but it's really the classes um, or how to think about them. Really, is that your total churn class is going to um, allow us to classify the complex vector bundles, and then the real bundles are the Pointryagin classes, and the characteristic classes in general are these specific obstructions to finding a single non-vanishing section of a bundle itself. So you can go through and further develop your intuition here. There's your Pointryagin classes. So these describe particular trivializations that give us obviously a lot of applications to studying the solutions of space-time, um, and in the Einstein sense. But yeah, so that's pretty much everything we have. Let's go back to just thinking about algebraic topology and differential forms. Just kind of like this intersection and why it's extremely leverageable. Because we start with local geometry, right? We define the rham cohomology from the core mathematical concepts of an exterior derivative, and this motivates gauge theory, source free fields. You can see all of this kind of emerge and justify topology and birth topological field theory. Then you also have the idea of regional type of patching that with the Vietoris and Cech theory that then becomes computable with algebraic decomposition of the cohomology with monopole patchings, local potentials as well. These are the types of things you want to relate to and ground the abstract mathematics in. So global twisting and characteristic types of classes as well that are important for instantons and topological QFT. And yeah, so this kind of is more the spectral sequences itself give us the machinery to define those and justify those invariants, those topological invariants, and then the characteristic classes themselves give us even further like ways to talk about vector bundles, and physically they would give us some more robust invariants that are interesting to us, and talk about conserved quantities from a more algebraic type standpoint as well. So thank you guys for watching. This was kind of a crazy episode. It was pretty challenging for me, but I'm willing to do this for you guys. So yeah, thank you so much, and I'll see you guys next time.